Hello, I'm Furkan, and I will give a presentation about nanotechnology and carbon within the scope of Introduction to Nanoscience and Nanotechnology course, which is a selective course at Mechanical Engineering Department of Ege University. Here's my overview. I will start my presentation with definitions of nanoscience and nanotechnology terms, and after I will make a comparison between nanoscience and nanotechnology terms. I will try to explain what exactly happens at the nanoscale and why are these happening. Then I will demonstrate the historical perspective of nanotechnology, and I will speak about three important scientists for nanotechnology: Richard Feynman, Taniguchi, and Eric Drexler. Then I will show one important invention for nanotechnology field. Then I will continue with nanomaterials and specifically carbon-based nanomaterials like fullerene, CNTs, graphene, carbon nanoonions, carbon nanofibers, carbon black, and nanodiamonds. Let's start with nano term. Nano refers to a scale of size in the metric system. It's used in scientific units to denote 1/1,000th of the base unit, approximately 100,000 times smaller than the diameter of a human hair. And here is a figure that shows some examples. For instance, a human DNA is 2.5 nanometers in diameter, and a sheet of newspaper is about 100,000 nanometers thick. Nanoscience is a new discipline concerned with the unique properties associated with nanomaterials, which are assemblies of atoms or molecules on a nanoscale. Nanoscience is actually the study of objects, particles, and its phenomena at a very small scale, ranging roughly from 1 to 100 nanometers. And here's the figure of nanoscale. And there is size comparison of objects like tennis ball, and nanomaterials like carbon nanotube and fullerene, and biomolecules like virus or bacterium, and this might be observed in this figure. Nanotechnology is the construction and use of functional structures designed from atomic or molecular scale with at least one characteristic dimension measured in nanometers. Their size allows them to exhibit novel and significantly improved physical, chemical, and biological properties, phenomena, and processes because of their size. Thus, nanotechnology can be defined as research and development that involves measuring and manipulating matter at the atomic, molecular, and supramolecular levels at scales measured in approximately 1 to 100 nanometers in at least one dimension. And here's the comparison of nanoscience and nanotechnology terms. The term nanotechnology is largely used as a reference for both these terms. But as mechanical engineers, we should distinguish between these two terms. Nanoscience is a convergence of physics, chemistry, materials science, and biology, which deals with the manipulation and characterization of matter on length scales between the molecular and the micron size. But on the other hand, nanotechnology is an emerging engineering discipline that applies methods from nanoscience to create products like other engineering disciplines too. What exactly happens at nanoscale is that the laws of physics operate in an unfamiliar way because of two important reasons. The first one is high surface to volume ratio, and the second one is quantum effect. The key reason for nanoscience regime being special is the dramatic increase in the surface to volume ratio. When the size of building blocks gets smaller, the surface area of the material increases by 6 orders of magnitude, while the volume remaining the same. And this situation, the exponential increase in the surface area, can be seen in the figure. Uh, Most behaviors change at nanoscale, such as reactivity, optical behaviors, and magnetism, because of these two key reasons. And this is the historical perspective. Even though we think nanotechnology is a recently discovered field, when we look from the historical perspective, we understand that people were using these phenomena about nanotechnology without knowing, even before Christ. For example, thousands of years before Christ, people used natural fabrics such as cotton, wool, and silk and processed them into products What makes these fabrics so special is that they developed a network of pores of size 1 to 20 nanometers for typical nanoporous materials, and these nanoporous materials can be seen in the figure left. Two more examples from history. The first one is wine producing process, which has a fermentation at nano level. And the second one is a cup from pre-Christian Romans. This cup has nanoparticles of silver and gold, over 90% in total. When the lightning source put inside the cup, it seems red and purple, but if we put it outside, we see it green. And this is father of nanotechnology, Richard Feynman. The concept of nanotechnology was first popularized by the Nobel laureate Richard Feynman. In his talk, "There's Plenty of Room at the Bottom" at the California Institute of Technology in 1959, Feynman spoke about the atomic level particles and their precision, and also he explained how these particles accurately follow the laws of physics and would have an enormous number of real-life applications. Although the idea of nanotechnology was introduced by Feynman, Taniguchi used it for the first time in 1974. He is a Japanese professor at Tokyo Science University. In 1974, in a conference paper entitled "On the Basic Concept of Nanotechnology", he used the term nanotechnology and he discussed the designing of various engineering materials at the nanoscale. And Eric Drexler, later in 1987, Eric Drexler, who is a graduate from MIT, published a book called "Engines of Creation: The Coming Era of Nanotechnology", which was directed towards the non-technical audience. This book primarily concentrated on what we can build by carefully arranging the atoms. And one important step for nanotechnology world, scanning tunneling microscope. In 1981, the IBM Zurich researchers developed scanning tunneling microscope, which gave access for the first time to the nanoscale world. I put this into my presentation because I think this is one of the most important inventions for nanotechnology world. Because this invention made it possible to understand the behavior of individual atoms and molecules when they are presented on an electrically conducting substrate. And after this invention, these two researchers got the Nobel Prize in Physics in 1986. After general information about nanoscience and nanotechnology, I want to continue with nanomaterials before talking about carbon-based nanomaterials. Nanomaterial means a material that meets at least one of the following criteria. One of them consists of particles with one or more external dimensions in the size range of 1 to 100 nanometers for more than 1% of their number. The other one is internal or surface structures in one or more dimensions in the size range of 1 to 100 nanometers. And the last one is specific surface to volume ratio should be higher than 60 meters square per centimeter cube, excluding materials consisting of particles with a size less than 1 nanometer. We can classify nanomaterials into various categories. One of them is based on dimensionality, and the other one is based on the type of material used. The classification of nanomaterials based on dimensionality basically depends on the number of dimensions of an object or material, which are not in the nanoscale range. The nanomaterials are broadly classified into four groups: zero-dimensional, one-dimensional, two-dimensional, and three-dimensional. And some materials belong to these groups can be seen in the figure. When it comes to the materials, nanomaterials are classified mainly into four categories based on their composition: carbon-based nanomaterials, metal-based nanomaterials, dendrimers, and nanocomposites. And during the rest of my presentation, I will talk about carbon-based nanomaterials. Before talking about carbon-based nanomaterials, I want to introduce carbon atom at first. Carbon is the third most abundant element in the universe after hydrogen and oxygen, respectively. Carbon, arguably, is the most fascinating element in the periodic table, having the ability to build itself and to nearly all elements. Carbon is important for many technological applications thanks to this binding ability, and in the figure, some properties of carbon atom can be observed. Here is some general information about carbon-based nanomaterials. In 1985, with the discovery of fullerenes, nanotechnology world took an important step. Discovery of fullerenes marked the beginning of an era of synthetic carbon allotropes, SCAs in short form, or better known as carbon nanomaterials. And after some time, new members added to this family like carbon nanotubes and graphene, and these materials can be seen in the illustration. And this is all types of carbon-based nanomaterials: fullerene, carbon nanotubes, graphene, carbon nano-onions, carbon nanofibers, carbon black, and nanodiamond. Firstly, I will introduce fullerene. As is the case with numerous important scientific discoveries, fullerenes were accidentally discovered. In 1985, Grotto and Smalley found strange results in mass spectra of evaporated carbon samples. Herewith, fullerenes were discovered and their stability in the gas phase was proven. The fullerenes, of which the smallest stable and the most prominent is C60, are molecular carbon allotropes. C60 consists of a spherical network of 60 structurally equivalent sp2 hybridized carbon atoms in the shape of a football composed of 12 pentagons and 20 hexagons. The C60 fullerene, in other words, Buckminster fullerene or buckyball, is the representative and approximately 0.7 nanometer in diameter. In the fullerene structure, all carbon sites are equivalent and the bond lengths are 0.14 nanometer for the double bond and 0.146 nanometers for the single bond. Here are some properties of fullerene. Fullerenes are large, closed-cage carbon clusters and have several special properties that were not found in any other compound before. Fullerenes are non-toxic and soluble in many organic solvents. Functionalization of fullerenes further enhances its solubility. Spherical curvature in fullerene molecules, however, produces angle strain that allows fullerenes to undergo characteristic reactions of addition to double bonds, thus forming a large number of derivatives known as fullerenes. C60 fullerene in organic solvents exhibits 5 stages of reversible oxidation reduction, thereby making it as either electrophiles or nucleophiles. This characteristic conjugation leads to the pronounced redox activity and imparts outstanding electronic properties. Application potentials of fullerene. Fullerenes in general form an interesting class of compounds that surely will be used in future technologies and applications. Physical and chemical properties may be tuned via the addition of element and molecular species into the fullerene lattice C59N within the gauge and at the center of C60, or coating the surface of fullerene with transition metals, thereby forming a variety of new fullerenes. Fullerene and its derivatives are considered potential candidates for a number of applications, such as being used for strengthening, hardening, and improving the electrical conductivity of alloys. Secondly, carbon nanotubes, shortly CNTs. Carbon nanotubes can be described as a rolled-up tubular shell of graphene sheet, one atom thick layer, which is made of benzene-type hexagonal rings of carbon atoms. The tubular shell is thus mainly made of hexagonal rings of carbon atoms, whereas the ends are capped by half dome-shaped, half-fullerene molecules. Due to their special one-dimensional form, they have interesting physical properties such as they have metallic or semiconducting electrical conductivity depending on the chirality of the carbon atoms in the tube. Nanotubes have a large geometric aspect ratio and they are the first nanocavities. This is the classification of CNTs. Carbon nanotubes are classified as single-walled carbon nanotubes and multi-walled carbon nanotubes. Their short form are SWCNTs and MWCNTs. Most SWCNTs have a diameter close to 1 nanometer with a tube length that can be many millions of times longer. That means they can be measured in meter scale. And MWCNTs are nanotubes with more than one graphene cylinder nested one into another. Typical MWCNTs have an inner diameter of 1 to 3 nanometers and an outer diameter of approximately 10 nanometers with the interlayer separation of 0.34 nanometers. When it comes to properties, based on the rolling direction, CNTs can be semiconductors or conductors. CNTs show extraordinary mechanical, electrical, and thermal properties because of their carbon-to-carbon covalent bonding and seamless hexagonal network architecture. Electronic, molecular, and structural properties of CNTs are determined to a large extent by their nearly 1D structure. The most important properties of carbon nanotubes and their molecular background are chemical reactivity, electrical conductivity, optical activity, and mechanical strength. Applications: CNTs are the most intensively researched nanomaterials and have great potential for numerous applications. CNTs are used in the plastics industry for composite materials, the electronics industry for display or conductive transparent films, the semiconductor industry for transistor channels, the energy industry for batteries or solar cells, and the biohealth industry for sensors. Small additions of nanomaterials such as CNTs can greatly improve structural properties of composite materials. Due to their electrical conductivity, CNTs also have application for the manufacture of low-cost solar cells, electronics, and anti-static composite materials. Thirdly, I will introduce graphene. Graphene, the youngest allotropes of elemental carbon, is a one-atom thick sheet of sp2 bonded carbon atoms in a hexagonal arrangement. Graphene is at the cutting edge of materials science and condensed matter physics research. It is the thinnest known material in the world and conceptually a basic building block for constructing many other carbon materials. It can be rolled into 1D CNTs and stacked into 3D graphite. With the addition of pentagons, it can be wrapped into a spherical fluorine. In one sense, it's the mother of all graphitic materials. And here are some unique properties of graphene. Charge carrier mobility. One of the most interesting properties of graphene is its high charge carrier mobility, which is independent of temperature. And the density of graphene is quite low, it's 0.77 milligrams per meter square. And optical transparency. Graphene is almost transparent, it absorbs only 2.3% of the light intensity. And the strength of graphene. As yet, graphene appears to be one of the strongest materials ever tested. Measurements have shown that graphene has a breaking strength 200 times greater than steel. And conductivity. Electrical conductivity is somewhat higher than the conductivity of copper, and graphene conducts heat 10 times better than copper. Graphene's applications. Graphene-based applications such as transparent electrodes, solar cells, and ultrafast photodetectors and phototransistors have been recently demonstrated. Since graphene is a transparent conductor, it can be used in applications such as touch screens, light panels, and solar cells, where it can replace the rather fragile and expensive indium tin oxide. Graphene is more flexible than steel. It's also a recyclable and sustainably manufacturable product that is eco-friendly and cost-effective in that would allow the development of lighter and stronger cars and planes that use less fuel. Flexible electronics and gas sensors are other potential applications of graphene. And now I will introduce carbon nanoonions, shortly CNOs. Carbon nanoonions, a fullerene-related material having concentric graphitic shells, represent another new allotropic nanophase of carbon materials. It's essentially a multi-wall fullerene since center shell is a C60 molecule. According to a recent study, CNOs can also be used to produce ultra-high power micrometer-sized supercapacitors due to their accessible external surface area for ion adsorption. In spite of the characteristic structure equivalent to MWCNTs with zero length, carbon nanoonions have never been isolated in macroscopic amounts, impeding physical or chemical characterization of bulk or dispersion properties. Now I will introduce carbon nanofibers. Nanofibers consist of the graphite sheet completely arranged in various orientations. One of the most outstanding features of these structures is the presence of plenty of sites, which in turn make sites available for chemical or physical interaction, especially adsorption. Carbon nanofiber can be obtained in size ranging from 5 to several hundred microns on length and between 100 and 300 nanometers in diameter. Applications of carbon nanofibers. The unique structure of these porous carbon nanofibers resulted in good electrochemical performance such as high reversible capacity and good cycle stability when they were used as anodes for rechargeable lithium batteries. Field electron emission sources, composite materials, scanning probe microscopy tips, and for electrode materials are the other examples of carbon nanofiber applications. Now I will give some information about carbon black. Carbon black is pure elemental carbon in the form of colloidal particles. It's produced by incomplete combustion or thermal decomposition of gaseous or liquid hydrocarbon under controlled conditions. The average particle size of carbon black is of a few nanometers. Essentially, carbon blacks are the pure soot and are produced by the pyrolysis of carbonaceous industrial waste. The applications. The primary use of carbon black is in rubber products, approximately 90%, mainly tires and other automotive rubber products such as hoses, gaskets, and coated tubes. About 9% of carbon black is used for pigment in toners and inks, and the remaining 1% is used as an ingredient in hundreds of diverse applications. Much smaller amounts of carbon black are used in the manufacture of dry cell batteries. Lastly, I will introduce nanodiamonds. Nanodiamonds are diamonds with a size below 1 micrometer. They can be produced by impact events such as an explosion or meteoritic impacts. Because of their inexpensive, large-scale synthesis, potential for surface functionalization, and high biocompatibility, nanodiamonds are widely investigated as a potential material in biological and electronic applications and quantum engineering. In 1963, Soviet scientists at the All-Union Research Institute of Technical Physics noticed that nanodiamonds were created by nuclear explosions that used carbon-based trigger explosives. Here are some properties of nanodiamonds. They are 50 times harder than titanium, and the other unique properties of nanodiamonds are thermal stability, chemical inertness, adsorption, optical properties, and biocompatibility. And the applications. In addition to geological and astrophysical interest, nanometer-sized diamonds have attracted the interest of the nanoscience and nanotechnology communities for the potential application of nanodiamond film as bright, low-voltage cathodes and light emitters, and of diamondoids as electron emitters. The exceptional hardness, fracture strength, and inertness of ultra-nanocrystalline diamond films, together with their smooth surface, make them unique materials for miniaturized mechanical systems and devices. The electrochemical properties of diamond make it an interesting material for sensing applications in sensor arrays and lab-on-a-chip. Due to the properties of non-toxicity and high biocompatibility, it has also attracted considerable attention on some new applications, especially in the biomedical fields such as imaging, diagnostics, and drug or gene delivery. The success of nanodiamond materials in biomedical applications stems from the fact that Many small molecules such as proteins, antibodies, therapeutics, and nucleic acids can bind electrostatically to the surface of nanodiamonds, making it an ideal candidate for use in drug delivery and surgical implants. And here are my references, the books that I've used for preparing this presentation. And this is my email address for contact. Thanks for watching me.